everyone. Today we'll be talking a bit about Fluss, a bit about CDC, and a bit about Paimon. So I'm Dominic, I come from Paurus, from Slovenia. It's a nice company, and if you come to Slovenia, of course, you should visit our beautiful city of Ljubljana. But we're not here about my country, we're here about, let's say, CDC. So why does CDC matter? Of course, there is a saying, when you take the car out of the dealership, it already lost half its value. So it's the same with data. The moment the data is created, it's good. The next moment, it lost its value. So where do we find this fresh data that we want for our reports, for our analytics? Well, it's the best to look at it at the source. And the source of most data in traditional databases is wall log, bin log, redo log. So basically, most of the traditional databases, they keep another file log. Before you do an insert into Postgres, it first goes to this log, because from that log, the whole database can be replicated if the log is, of course, available. So in this case, the most fresh data that we can be found in the wall log. And of course, it's nice to have such things. And well, it's important for the CDC, it's also important for the database itself. So it was not invented for the CDC, but it was invented for replication. So for example, Postgres replication writes to the log, and it has a special process that sends chunks of this log to other Postgres replicas. Why is this important? Because we can pretend to be a Postgres replica to get a copy of all the data, or better, not the data, but the change log itself, so we can know what happened to each table. Nice thing about Postgres is it also has publications, so we can define which exact tables, which exact data we want to see, we want to send to us. So this enables, of course, replicas that only contain some tables, and this can offload resources for the main Postgres. But again, we're not here about Postgres. It's a nice feature that we can use as well. And of course, the data that is retained in the Postgres is stored there safely. The wall log is stored safely until all the registered consumers didn't read that data. That means if our, let's say, Flink cluster is shut down, the Postgres database will not delete the replication log until we connect it again, if of course the replication slot is still alive. So when we are talking about replication logs, the honorable mention here is the Bezium. It's the go-to platform for real-time streaming of these replication logs. It has many connectors. Red Hat has been maintaining it for quite some time. Of course, it was made to work with Kafka Connect. Hopefully, most of you know Kafka Connect, but that comes with another cost. You have to run a Kafka Connect cluster, and you have to put all the data that you get from the database into a Kafka topic with some rules that you set in the Kafka Connect. Of course, this comes with fault tolerant and scalability and everything, but the most important thing, at least for our company, it was that it's not intrusive. So Postgres doesn't suffer much performance impact, more or less it's negligible, so you just connect a replication slot there, and everything works on the Postgres as well, and the core team, let's say, that's developing the product on Postgres doesn't even know that you're there. They know if Flink is down for some time and wall log keeps growing, but usually they don't feel it. And of course, the Bezium, since it's built based on replication, it can enable exactly once delivery, which is also nice because we save the cost of the duplication on our forward streams. So the Bezium also has a nice things, because we all know that we don't start every project from scratch. You get somewhere, you say, oh, now we need CDC, what do we do? The database already has data. So for these cases, the Bezium also has snapshotting. So it can first read the table that you want to stream, and then the streaming starts when the table was read fully. The nice part about this is that it saves the log position from the moment it started reading the table. So even if it's reading the table for an hour, it will start from before that hour, not after, so no data should be lost. It also has some ways to parallelize this and to read multiple tables, etc. And of course, we get all of this in the stream. So what can we do with the Bezium in Flink? The Bezium is set usually in Kafka Connect, but they have a mode to run it directly in Flink or other Java stuff. It's like a library. So you get to have the core of the Bezium right inside your Flink, and it's a nice connector under the Flink CDC repo on GitHub. and you can use it to get your source of data right from the Postgres. So no need for Kafka, no need for additional Kafka Connect cluster. You can get it directly in Flink. And it's called embedded mode, just to be clear. Now, of course, with Flink, we also get data stream API. We have SQL API, so we can compare those two a bit. In the SQL one, the table creation is quite simple. You specify the connector. I mean, usernames and passwords are standard for the databases. As I mentioned before, you can have publications, but I did not mention them here, sadly. And of course, the important thing is the slot name, because each database that is replicated from, let's say, Postgres has its own replication slot. So Flink can have his own. You can have multiple replication slots. For example, if you wanted to just have one stream for users, one stream for orders, you could have 2 replication slots. Not that I recommend many replication slots, but it is possible. But of course, SQL is easier to set up, while it does not give that much flexibility. And of course, at least last time we were dabbling with SQL, you had more or less one table, or I guess multiple tables in some weird format, which might not be as efficient as one might like. And that's where data stream comes in, because you can have multiple tables, even for multiple schemas on Postgres databases, if that's your thing. And the nice thing is you can implement your own deserialization schema. So what this means, you get a serialized data, and you don't have to convert it to JSON, convert it to anything. You can read raw data. This is nice, especially because everybody likes performance, and if you read raw data instead of converting to JSON, converting to records, it's of course more performant. And of course, with data stream fine-tuning, you can have exactly what you want. You don't have to deal with, oh, I got this in the package as well and I have to use it. You can configure everything. So if you use CDC but don't have your own deserialization schema, I would advise it. It's very nice with Java generics. You can have one deserialization for multiple tables, etc. But you have to be a bit of a Java developer for that. So again, complexity. So the structure of the Debezium is quite simple. You get an operation. You can get before data. You can get after data. Usually only after data is needed. But if you want the before state, you have to set, at least in Postgres, replica identity to full. This means that Postgres will identify its row with the whole row. It sounds weird, but this is the only way to get the whole row that was before the update and the whole row after the update. This does have a slight penalty on performance on Postgres, so if you don't need it, please don't set it. But they did in version 17 give some improvements in that area as well, so it might not be as hard as it was back in the days. And of course, if you don't need some of the fields, it can be adjusted in configuration as well. So, of course, pruning everything beforehand is more efficient. So what now? We have the data. What can we do with it? So syncing this data, of course, lots of incremental updates is not ideal for a normal database, of course, because we have a lot of data. Again, it's not ideal to just use a file format like Iceberg. You can, it's not ideal, because most of those stuff is either very oriented towards transactions or very much oriented to the disk level and only appending and not updating things. This is where Fluss comes in very nicely. It was created a sort of a hot storage for Flink. So on one hand, you can imagine it like if you have your job state and you can externalize it to some other thing. So it has two things that are worth mentioning. This is columnar storage. You know Kafka, you can compare it to Kafka if you want. So Kafka is streaming data, but the schema you have to define yourself. You can have Aura files, etc. But the Kafka itself is not schema aware. Fluss is schema aware. This means that projection pushdown works, but we'll touch this a bit later. Of course, the project is currently incubating, so it might have some things that are yet to be delivered. Similarity with Kafka, of course, is logical, although we have to be careful because Kafka has topics, Fluss has tables, so it sounds the same, but the underlying architecture is quite different. You don't have independent brokers, you have coordination manager and tablet servers, for example, so there's even architectural change, so they did not just copy Kafka. And you have two types of tables. The first one would be log table. This one is only for incremental data. On one end, you're writing incremental, so append only into the table, and on the other hand, you're reading this data. So it acts similar to Kafka. And of course, columnar pruning is a big thing here. And another thing is a primary key table that is built on top of the log table. So this is quite nice because when you have a primary key table, it acts kind of a key value storage. Now, currently, of course, even of course in data stream API, when you have a lot of freedom, you can implement your own connectors to key value storage, maybe even some Hazelcast cache or something in memory. But when you're using SQL API, there are not that many options. And when you're implementing some things on your own, you get Lambda architecture, which not many people like, and Flink is made for Kappa architecture better. So the nice things of a primary table is a materialized view of your data. So everything you put in it can be found on the main key. And of course, when you can read data on the other end as well, because it's basically a log table with some RocksDB storage. So you get Kafka with RocksDB table with key value storage. And the nice things, of course, if you compare it to some other key value storages, it gets partial key lookups. So you don't have to have exact key. You can have only parts of that key. Of course, you need to have the main part, so the column that is used for replication, that one more or less has to be there, so you know where to look. But other things can be only partially there, of course, in the right order. And this gives us a lot of flexibility that other systems usually don't have. And another nice thing is that I mentioned before how Postgres has another setting, so you get before updates and you get after the update. Fluss emits both. Out of the box, you get -u for what the data was before the update and u for after the update. And of course, when you're inserting, when you're deleting for this, from this table, you don't have to provide all the columns, so you have something null, there's a merge engine behind, and it will take care of this so that you're not overriding something with null data if you don't have. So you don't only need one sink, you can sink multiple things into the same table if you want, and the data, if you set it up correctly, of course, won't be overwritten with null values. So again, Flink SQL, it's quick. You have to, of course, make a new catalog, same for some other stuff. And the table creation is simple. The data types are the same, I think, as Paimon. There was, of course, quite a few Paimon influence. And as I mentioned, it's partitioned. And in this case, this is a primary key table because we set up a primary key. If you don't set it up, in that case, you will have a normal log table that will be just streaming your data. And of course, sadly, it just came into last version. Okay, the joins, yes, sorry, I'm skipping a bit. So with Flink SQL, there was quite some issues with joining streams because your state could grow quite large. And if you needed one large stream to enrich another large stream with lots of data, of course, your state would explode. Your checkpoints would take quite some time. But luckily, Fluss can be used just like other Flink tables. As I said, it's materialized, so you can get point-in-time joins, and it will look up each value, of course, in the Fluss. Fluss even has storage tiering, so if the data is hot, the lookup will be very fast. Of course, we know that Flink state is made with RocksDB, so Fluss is made with RocksDB, so actually it's not that much of a penalty to use an external system, but a lot of benefit from not having to manage huge state in your Flink job. Of course, I was mentioning data stream before. Here things are a bit more complicated. And the support for this actually just came in the last version, so version 0.07. Of course, every Java developer that uses data stream would be happier if data stream was, let's say, a higher priority on the roadmap. But still, we finally got our Fluss source and, of course, the sink as well. So again, you have to implement some things on your own. Like we did with the Debezium, you have to use the deserialization. But in this case, there may be some things that could be nicely implemented. For example, I intentionally did a long and an integer. So with normal, let's say, JDBC converters, when you read something from the database, it doesn't really care if it's an integer that was read, it can write it into long. Here you get some exceptions, because if you read a long to set long, and in the data table there's only an integer type, not big integer, that is converted to long, you get an error. So you have to be careful about your schema, although it's a nice thing that the schema is enforced. Key value lookup is possible, of course. They added another API for that. But it's a bit messy because it's a bit coupled with some administration API that is meant to create tables, etc. So you first have to find your database, find your table, and then on table you do some lookups. It will get better support, I'm sure, but currently, if you want to do this, you will have to do quite a few experimenting on your own. Now, the most important thing for me, why we moved to Fluss, was pushdown. So when you have a normal Kafka topic, for example, with CDC data, you read the whole table, and of course the core team knows why they have 10 columns in the table, but maybe you only need 3 of them. And in case of CDC, you get all 10 of them. Now what to do? You can filter it out in the early Flink job, as we talked before, but what if you'll need them later on? It would be nice to store them. And in that case, you would have to filter it for some use cases and store the whole thing, or perhaps you have 2 use cases. I threw some simple jobs here that would need different parts of data. So one option is to have one job and do everything in one job. This way you can get fine control, you can get faster results. But we had one of those huge jobs that became quite painful to maintain. So splitting it again is a great option if you have a nice layer that can connect them. And Kafka might not be the best layer because you have a lot of or data duplication or excess data that you don't need. So pushdown is a way that you can specify, like we did here with projection fields. I only need ID, age, and name when I'm reading from this source. And this would mean that even if we have a lot more data in Fluss, only those columns would be read. On the roadmap, they even have some filters that they want to push down, which will bring even more improvements. For example, you could filter out only female customers if you wanted, and you would reduce your data consumption network cost by half if you wanted to do such analytics. So it's very important, but sadly, or that's a good thing, of course, for me as a Java developer, you have to have predefined schema. So you cannot have a Kafka topic with now one type of objects, then you can have some other type of objects and some quasi-if sentences that can juggle between this. You need to define a schema. So Fluss is schema aware. It's aware that its table contains those fields and it can do a lot of those fields. Another great thing about the schema is also compression, because Fluss is aware that one column will have like comparable data. It can compress it in a columnar matter. And even the storage that Fluss does is in Arrow, and Arrow at the end of the day has batches of columnar data. That might not be the best for reading, of course, because when you do push down, you have to check every batch and then only read the column you want. For example, Parquet saves everything in one column in a line, so you don't, when you read the metadata and know where the column is, you don't even need others. With Arrow IPC, you need to have to read every batch in its own metadata, but still, it's way better than having to read everything. And this is a very nice thing and a selling point, at least for us. Now we've talked about Fluss. It has hot data. And eventually, if you get lots of data, again, Fluss might not be the best solution because there's too much data. And you don't want all the data to be hot. For example, data from last year does not need to be nowhere close to memory. And in those cases, we have table formats, of course. And before, you have to manually put the data into your table format and manually put data into, I don't know, Kafka, Fluss, or whatever. But in this case, Fluss can be backed by Paimon. This means that by adding 1 or 2 settings, Fluss will automatically move its old data or cold data into Paimon. And as I mentioned before, Fluss was made for key value lookups. If you want to do analytics and filters, this is currently not supported by Fluss, but it's supported on Paimon. So if you can live with your analytics data being 10 seconds cold, or a few more, you can query Paimon, and the Fluss will get the data automatically there. And again, this is a nice shift from the Lambda architecture where you had to do both cold and hot data. Fluss can handle everything for you. Of course, Paimon was made for batch, it was made for streaming as well. And among the table formats is, I think, the best for the streaming CDC data because of the nature of the incremental updates of the data. Other file formats are better handled by batch. And of course, it provides some ACID transactions, which is also nice because you can have data consistency and you don't have to worry about your data on the disk. And the compaction and merge processes help you save cost with data because as data gets even colder, Paimon compresses it and you don't have to worry about that, of course, if your settings were correct. As I mentioned, those two things are now connected. Of course, you can use Paimon on your own, but having Fluss on top of it can act as a sort of a caching layer because if you want to stream from Paimon, of course, you will get slower performance compared to streaming from something that has hot data in memory and can provide it as fast as Kafka, let's say, or at a comparable architecture. So Paimon with a data lake, you can store cold data, or better, Fluss will store cold data there. Fluss will have hot data, it will have some change logs, and you can consume change log from Fluss, which is also very nice. And the best part is it's invisible to the user. Sadly, it's invisible only to the SQL users, but let's face it, most of the stuff can be done in SQL, and some simple things don't need Java abstractions to be built. But does it just work out of the box? Of course, nothing works out of the box. And for Fluss to offload data to Paimon, you actually have to run a Flink job. They provide it as well, but you have to run it. And then on your Flink cluster, there's a job slowly running, talking with Fluss and asking, oh, do you have any data for me to persist? Fluss says yes. You can go check there on that storage, and that Flink job will slowly be moving data into Paimon. So again, Fluss was not made for computing things. We have Flink for that, and they moved compute to Flink, which is a very nice solution. But it's good to know that it won't come out of the box. You have to tick a switch for it. So what did we forget? I didn't show you any alter tables because there isn't any. So currently, Fluss doesn't have schema evolution. You cannot add anything once the table is created, which is a bit problematic. This is especially problematic if your data changes a lot. But I guess if you're not building something new, if you're adapting an existing system where you know the data will not change much, you can start experimenting with it. And I mean, even if there are problems and something new occurs, you can always copy data with another Flink job. You will live through it, and it will work. And so far, no support for Flink 2.0. I'm really looking forward to that because we already started to move our cluster towards it. And still, because it's incubating, it will get there, don't worry. It doesn't support things like arrays, maps, etc., or some custom binary data. It will in the future, but let's not jump right into it, perhaps, if you're missing those things. Again, the most senior answer here is it depends. Of course, if you don't currently have issues with huge states, if you currently don't have issues with performance, you can be more conservative about switching. On the other hand, if there's a lot of problems with state management and the 2.0 disaggregated state didn't help you much, you should check out Fluss. Of course, if you already migrated to 2.0, there's no point in switching back. You will wait for it to be adapted. And of course, if you're using DataStream API and don't want too much headaches, perhaps this should just be checked out, but not really encouraged, or better, you can encourage usage of Flink SQL. That would be about it for now. If you have any questions, the microphone will go around. And that's it. Thank you.